Hello, everyone. This is the second part of the lecture on this Wednesday, November 10th. In the first part of the lecture today, we discussed the derivation of the Boltzmann equation from the Liouville equation, just by taking the integral, momentum integral of the phase space distribution. And general Boltzmann equation has been derived, and now we're focusing on the 2-2 annihilation channel for dark matter. So the Boltzmann equation, the corresponding Boltzmann equation given here in the limit of no stimulate emission or Pauli blocking, as we discussed before. And we are going to take the Maxwell-Boltzmann distribution for the standard model particles. So these are also a good approximation. And so here, now we are going to go on one more step to simplify this Boltzmann equation for the 2-2 channel. The first, we can take the phase space distribution for the standard model particles to be Maxwell Boltzmann in this form, just the exponential to the energy divided by temperature. And we are ignoring the chemical potential in our discussion, the chemical potential equal to 0. And due to the energy conservation, after annihilation, sum of the dark matter energy is equal to sum of the standard model particles, sum of the energies for the standard model particles. Then the product of the phase space distribution for the standard model particles given by this exponential, and you can replace this sum of the energy for the standard model particles by sum of the dark matter, sum of the energies for the dark matter particles. Then this is nothing but the phase space product of the phase space distribution in equilibrium for dark matter. And also there's one more step to make a relation between the phase space distribution out of equilibrium in general, the phase space distribution for dark matter is not doesn't need to be in thermal equilibrium, and the ratio of the phase space distribution for dark matter to the one in equilibrium can be related, approximated to the dark matter number density divided by the one in equilibrium. So similarly for anti-dark matter, you can make such a similar approximation. Then here the Boltzmann equation, this phase space distribution appearing inside momentum integral can be rewritten in this form. The second term for the standard model part can be replaced by those for dark matter in equilibrium, and this phase space distribution in the first term can be replaced by the product of the number densities. So then you can go back to the formula for the Boltzmann equation, and you can just pull out these equilibrium densities out of momentum integral in front of the momentum integral to express this just to dark matter number density square minus n equilibrium square. Then so because this number density is already averaged over the momentum, so this number density square minus an equilibrium square can be factored out from the momentum integral. And then just do this momentum integral for the final state, psi bar, standard model particles. This is nothing but the formula for the cross section. So this the vector in front of the cross section is nothing but a Miller vector called Miller flux vector. So the cross section is defined as the number of scattered events, but divided by incoming particles, the flux of the incoming particles. So this Miller flux vector takes account of the incoming, the flux for the incoming particles. So in any case, then you can identify the coefficient of this number density square as the averaged annihilation cross section. So this averaged annihilation cross section can be written in this form. So we had the Miller flux factor, and here, right, the relative velocity just inside the parenthesis together with the cross section, and here the momentum integral, phase space integral contains 1 over energy twice energy. So those energies in the denominator cancelled by those coming from the Miller flux factor. So we are left with only momentum integral. And then of course there is the degree of freedom in the phase space integral, but those degree of freedom are cancelled, those appearing in the denominator in the equilibrium number density. So just you only have to take the momentum integral weighted by this cross section. So just average the cross section time the relative velocity between the dark matter particles, and just you divide by this momentum integral without cross section in the denominator. So okay, so this is this is general form of the Boltzmann equation. And averaged, you need to first calculate this cross section from particle physics and average over dark matter phase space distribution. Then you can get the average cross section, because in the cosmology in the early universe, the dark matter has velocity distribution. So just it's not a single velocity. So we need to consider distribution, the velocity distribution of dark matter, and depending on the velocity, depending on this velocity dependence of the annihilation cross section, you need to take this thermal average, called thermal average, to be taken into account. So average means thermal average. Sometimes thermal average is very important. And then this Boltzmann equation also can be written in a more actually more attractive, in a more attractive form by introducing yield instead of number density itself, or abundance. So this yield is the number of particles left after freeze out. When the dark matter does not annihilate anymore, you can fix number of dark matter particles. Then this yield defines number of particles, number of dark matter particles left after freeze out. So this y chi, and this is the y chi defined as the number density for dark matter divided by entropy density. So this S is the entropy density. So this entropy density is small. S is the defined as the energy density plus pressure divided by temperature. So this energy density and pressure is those in equilibrium, thermal equilibrium. So for radiation domination, P equal to 1/3 energy density. So you will get 4/3 times rho over temperature. And the radiation energy density given by the sum over pi square divided by 30 times Gi, and actually degree of freedom, and maybe I may have to divide this contribution. So it's okay. Let me use another line. So energy density, radiation energy density given by this. So I equal to boson. In the case of boson, maybe we can define temperature for each species. For chromium, we have 7/8 factor. So this is the radiation energy density with a given temperature. So this is the relativistic but not all the relativistic degrees of freedom in thermal equilibrium. So when we compute the entropy density, we need to consider. So these are all the relativistic for the energy density, all the relativistic species contribute, but among the relativistic species, those are in thermal equilibrium. Those contribute to the entropy density. And therefore, the entropy density, by using this equation, we got this. And this, okay. Okay. Then, what else I have to do? So here, of course, the this entropy density, this T, doesn't have to be the same temperature. So entropy can be defined for the system with equal temperature. So I think that it's better to write in this form. So energy density sum over this is the kind of generalization of the entropy density to the systems with the different temperatures. So then you see that instead of T to the fourth, we have T to the T cubed appearing in the definition for the entropy density. Okay, so then 2 so then we also define as G star S, so kind of effective degree of freedom contributing to the entropy density, and normalized by this photon temperature. This is T, so photon temperature. And then therefore this G star S equal to Ti over T Q plus 7/8. Something like that, yes. So this is the effective relativistic degree of freedom contributing to entropy in thermal equilibrium. Because it is possible for the light particles to be out of equilibrium, then it doesn't follow, it doesn't contribute to the energy entropy density anymore. It's decoupled. So then if Ti, they are all equal to photon temperature, they are equilibrium with a photon, then G star simply given by the sum of the degrees of freedom. Okay, so in any case, the entropy, so this, as I said, this as small as is the entropy density. So the total entropy in the universe, S is given by some or less times volume of the space-time, which is constant. Total entropy is conserved in the universe. Then from there, we can find that the G star T cube A cube equal to constant. Okay, so G star is, sorry, this is G star is. Therefore, the temperature, photon temperature, is proportional, inversely proportional to inverse 1/3 G star over minus 1/3 times inverse scale factor, the photon temperature. So if this G star is temperature dependent, you need to take into account the change of the effective degree of freedom when you compute at the photon temperature. Okay, so I mean, this is the also important for some cases, but here for our discussion, it's not that important because we assume during we can assume that the G star doesn't change much during the freeze out. So you can take G star to be constant for most of time. And then because of this definition, okay, and also the fact that this entropy density times scale factors cube, A cube is constant, we can show that time derivative of yield, Y, is given by this, and this is the okay, so and then this entropy density, time dependence of the entropy density is nothing but minus 3 Hubble constant and entropy density. So this is the time derivative of the number density time plus 3 times Hubble parameter times number density. So this quantity in the parentheses appears in the Boltzmann equation in this combination. Therefore, the Boltzmann equation can be rewritten. So this quantity in the parentheses is S times time derivative of yield, which is equal to average cross section, and we have the n square, number density square on the right hand side. So take into account we are replacing the number density by yield. So we just replace number density by yield. Okay, so therefore, then we have a simpler looking formula. In this form, the Boltzmann equation is now just the time derivative of the yield, and the yield changes being proportional to this annihilation term. If there is no annihilation, just the yield, the total number of the dark matter particle remains. So why yield is total number of dark matter particles? Because the for relativistic dark matter particle, if in the limit of relativistic dark matter particles, or maybe it's better to say this way. So after freeze out, the dark matter number density, the dark matter is like a metal-like, and the number density scaled by scale factor. So dark matter mass times, the number density is the scale by 1 over volume, A cube, and this volume, A is the temperature Q. So entropy density scale by T cube. So the number density of dark matter particles after freeze out scaled by T cube, and also entropy density scaled by T cube. So this ratio of the dark matter number density divided by entropy remain the same after freeze out. Of course, this in front of the T cube in the entropy density, this effective relativistic degrees of freedom changes as a function of temperature. So because of that, this is true. I mean, the ratio of these quantities remain constant as far as entropy is not changes. So entropy G star S is constant. So we're going to take into account the change of entropy in the later discussion. So in any case, this is why we are taking the ratio of the dark matter number density to the entropy density. And okay, so now we are changing a variable from T to T2, the temperature, and then T, the temperature, I mean this, okay, so, okay, so what can I do? So from the Hubble parameter, so Hubble parameter as a function of T or temperature. So Hubble parameter is given by this. Temperature scale divided by Planck scale, and during radiation, this is given by 1/2T, right? So, and then on the left-hand side, we can change from T to X parameter. X is the defined as this one, and we call, so by defining inverse temperature by X, so this is new variable from T to X. And then this is the just the quantity in front, nothing but the Hubble parameter evaluated at the dark matter mass when the temperature is equal to dark matter mass. So then this quantity from there, this is the equal to 1/2T. Therefore, dt equal to so from there, so T equal to twice okay, so okay. Okay, so time can be written in this form, 1/2 Hubble parameter and times x squared. Then dt, the derivative dt d over dt equal to so this is the yeah, this is just a simple change of variable. But, okay, so let me put it this change of variable from t to x into the Boltzmann equation that we derived here. Then the Boltzmann equation becomes then y yield and y yield in equilibrium. Okay, so and also here the entropy density can be written. So because entropy density is proportional to temperature Q, so we can define entropy density T over M chi Q. This is the nothing but entropy density evaluated at temperature equal to dark matter mass times x minus Q. So I think this one is not inverse, this is just x. So therefore, eventually, you can obtain this simple equation. So this is Boltzmann equation you need to solve for given initial condition for yield. So in the beginning, we suppose that the matter in thermal equilibrium. So we can start from some equilibrium initial condition for the dark matter number density must be equilibrium number density at that temperature. So Ti equal to m chi divided by initial temperature. This is because this is the first order differential equation. You can, in principle, solve this first order differential equation with the only one initial condition, and then from there, when temperature equal to 0 at current universe, you can obtain yield at present by taking x to infinity or temperature to 0. Then you obtain the dark matter relative density. So this is what we are going to do. So here we are calling the coefficient here, and we call this as lambda function of x. Although this free factor, the entropy density divided by Hubble parameter, this quantity is independent of x or temperature. It is possible that this dark matter annihilation cross section can depend on the temperature in general. Okay, so now we are going to discuss the several things, how to solve the Boltzmann equation analytically, and how to determine when dark matter becomes out of equilibrium, the so-called freeze-out temperature. So freeze-out condition can be easily identified. And before going to discuss, let me first remind you yield y in equilibrium. First, and then when a dark matter does not annihilate any further, then the dark matter becomes out of equilibrium. So then the yield for dark matter can be different from the one in thermal equilibrium. So it is important to know what is the yield in thermal equilibrium first. So there are two cases when dark matter temperature is very high. So this is the temperature. Okay, temperature is larger than dark matter mass. So relativistic case. Then we need to take the number density for relativistic case. So G effective is the effective degree of freedom for dark matter. And TQ and entropy density given by this formula. So T cube, they are all canceled out to give you certain fixed number. Of course, this G star, the effective relativistic degree of freedom in thermal equilibrium depends on temperature. So once you fixed the temperature, then just almost independent of temperature, fixed number. So it is a very large number, 0.2 something. On the other hand, in the case of non-relativistic, and temperature is much smaller than dark matter mass, that is the non-relativistic limit, then we need to take the number density for dark matter in the non-relativistic case. Okay, then this one is the 0.145 G effective G star ST times x 3/2 x to the 3/2 times e to the minus x. So as you can see, the equilibrium yield for non-relativistic, there is a Boltzmann suppression. Of course, if dark matter keeps in thermal equilibrium at high temperature, dark matter number density is almost constant. But as the temperature drops, dark matter becomes non-relativistic. And suppose the dark matter keeps in thermal equilibrium, the dark matter yield will be suppressed. Dark matter will just disappears. So you can draw yield in thermal equilibrium as function of x. Sorry, this is x. X, large x means small temperature. So that this is the, just to follow this curve. So this is the exponential suppression can be explained by this Boltzmann suppression. So here at high temperature, and x is very large, small, sorry, x is very small. And this is the exponential fall off is for large x. Then you need to break, you need to out of equilibrium because of this behavior at low temperature. Otherwise, there is no yield. In the end, there is no dark matter particle left after all. So we need to consider freeze out. So then we need to consider freeze out mechanism to determine finite yield at the freeze out temperature. But this finite yield must be consistent with the observation for dark matter number density. Okay, just we want to massage a little bit on the Boltzmann equation of the original form in order to see what is the freeze-out condition to be. Actually, yeah, so this is the Boltzmann equation that we have derived before. So here just to we make this all the quantity like entropy density and Hall parameter to be temperature dependent. Then this from there, I think that this is the we need to replace this x over h by this one. So then you will get this expression. This entropy density and Hubble parameter, they are all it's a function. They are all function of temperature in this expression. Then from there, you can divide by yield and equilibrium. Divide both sides by the yield in equilibrium. And then leaving only one equilibrium number density explicitly appearing in this formula, then we can write down, rewrite this Boltzmann equation in this form. And we call this dark matter number density in equilibrium times annihilation cross section called gamma A. This is the annihilation rate. And of course, this Hubble parameter is the expansion rate. So inverse of annihilation rate determines the time scale for the annihilation, and inverse Hubble expansion rate is the expansion rate, inverse expansion, the time scale for the expansion. So on the annihilation rate divided by Hubble rate, so this is one, this is the, therefore, if the yield change in yield is proportional to this formula, and this is the nothing but the yield change in yield the yield does not change much, then this is the condition for the freeze out. Is meaning that the yield does not change from that time on. So this is the condition for the freeze out. So gamma A in equilibrium is the comparable when this annihilation is comparable to the Hubble rate, and you are the dark matter becomes out of equilibrium or frozen. Dark matter number density is frozen. So just to keep in mind, this is condition, the freeze out condition. In the reality, the more precise calculation of the freeze out temperature. So this condition gives rise to the freeze out temperature. So this freeze out temperature, because the Hubble parameter is a function of temperature, and the dark matter number density also a function of temperature. So you can solve for temperature. By solving this equation, you can obtain the freeze out temperature. This is a rough kind of estimation of the freeze out temperature. Okay, so we discussed the freeze out condition for dark matter. Then after that, dark matter yield does not change anymore because of that. Dark matter yield if there were no freeze out, the dark matter yield will follow the curve for the equilibrium case, but the yield does not change. At some point, which is around the freeze out temperature XF, then the dark matter becomes frozen. So this is the freeze out temperature, dark matter yield. So this is the constant. So those then the curve will become like, it will follow the equilibrium curve and becomes out of equilibrium. So this is in equilibrium, and this is the out of equilibrium or freeze out. Okay, so then how to determine the dark matter number density, and what is the more precise estimation of the dark matter, the freeze out temperature. Okay, so okay, I think that this discussion takes some time. So just to suppose we have determined dark matter yield. So when the dark matter becomes out of equilibrium, the freeze out, and when at the time of freeze out, suppose dark matter becomes non-relativistic at freeze out. This is the case in most cases. This is true for most cases. Then dark matter yield at infinite x is given by roughly the equilibrium number density, equilibrium yield at the freeze out temperature, which is given by this. This one, and x, the freeze out. Okay, so because of this, there is the Boltzmann suppression due to the exponential. So when we solve the Boltzmann equation, we need to know what is the velocity dependence. I'm sorry, what is the temperature dependence of this cross section? We just parameterize this annihilation cross section by this annihilation cross section as a function of inverse x to the minus n. So as you remember, x equal to x to the n is nothing but temperature divided by dark matter mass to the n. So this is roughly velocity square nth power of the velocity, average velocity. So then if there is a velocity dependence in the annihilation cross-section, you need to consider velocity dependence and in the average. So just we are parameterizing the annihilation cross-section in this way. And as n equal to 0, then we call S wave. Then in this case, dark matter annihilation cross-section is independent of velocity in the leading order. And if n equal to 1, we call this as P wave, the velocity dependent, and velocity suppression. There's velocity suppression. So in that case, Boltzmann equation can be written in this way. And here lambda is a constant parameter. And this is just given by several constant values. Okay, so this cross-section lambda depends on cross-section and Planck mass, dark matter mass, the non-relativistic degrees of freedom in thermal equilibrium, etc., etc. The lambda is constant value. This is constant. So particle physics, we only have to know the dark matter mass and cross-section. Then we can solve the Boltzmann equation for the yield. Okay, today we don't have much time for the further discussion. We will continue our discussion on the solution to the Boltzmann equation next week. Okay, thank you.